The center frequency of this band is 14.175, so I'm going to change this 14175. Push enter, click calculate, click wire edit. I'm going to draw the loop at YZ axis. The beaming direction of this antenna is going towards X plus X axis. From preliminary calculation, each side of the loop is 5 meters long. So click new loop here. We are going to draw around this center coordinate here. Okay, so this is information for wire number 4, signed by red color here. The length already 5 meters, and wire number 1 also 5 meters, wire number 2 also 5 meters, and wire number 3 also 5 meters. Click OK. You could see the detail here at geometry. Okay, this is already right. 2.5 meters from center coordinate. Okay, and 2.5 plus 2.5, totally 5 meters. If you are getting different value here, you could edit from here. This is to enter value for radius of element. Radius is half of diameter. The value here 0.8 millimeter, so the diameter is 1.6 millimeter. I keep the value here. Okay, because we are going to design antenna with horizontal polarization, so the feed point is going to be put here at the center of bottom side here. This is wire number 1. So back to geometry. We are going to give simulating pulse here. The variable is W1C, stands for wire number 1 at the center. You could see how to use this variable at the MMANA-GAL manual. Just push enter, and now click calculate. The ground, it is not free space, it is not perfect, but it is real. So click ground setup here. The soil, I'm going to put the antenna as have the characteristics of dry field and forest. According to the manual, the electric value is 13 and conductivity is 5. This value already correct here. I just click OK. And now the height is 10 meters. You could change the value, but I'll design for 10 meter high. 10 meters high is from ground to this center coordinate. In reality, it is to the boom. For material, I'm going to use copper wire, so just choose CU wire here. Now we are going to start the SWR simulation for this preliminary design. Click start. The SWR is quite high. It is 22.14. The ideal SWR is 1. With this very high SWR, I think most of the power is reflected back from the feed point back to the transmitter. So we are going to optimize this. Click optimization. There are several variables that we could optimize. First is gain. Most of the designers like to have maximum gain at the antenna. So slide here to the right for maximum gain. But theoretically if you like to have maximum gain, the front to back ratio will be less, and vice versa. If you like to get maximum front to back ratio, then gain would be less. So put here at the minimum front to back ratio to get maximum gain. This is optimization for elevation angle. The ideal elevation angle is 0 degree or parallel to the ground. So the maximum distance would be maximum if reflected by ionosphere. So to get minimum elevation degree, slide it to right here. This is optimization for JX. JX is reactance part of the antenna impedance. The ideal value is 0 to get 0 or no reactance at the antenna impedance. Slide it to right. The SWR, to get the SWR1, slide to the right, and also matchness also slide to the right. You don't have to consider this current, keep it here. The optimization is going to be to the whole element, so click all elements and then click start here. You see here now the SWR is 2.72, much better, although not 1. The beaming pattern of this one element quad is to the front and to the back but not to the side, to the both side. Now we are going to design second element. If you are going to just design 2 element beam antenna, so better to use reflector rather than director, because reflector has higher gain compared to director. Usually between element the distance is 0.15 lambda. So for 20 meters bend, around 3 meters. So we are going to use this geometry to add the reflector element. So the wire will be number 5, 6, 7, 8. Okay, now we are going to enter the value here, and for the reflector element, the dimension is about 5% longer compared to driven element. So the distance is it's going to be put at the minus x axis, minus 3.0. Okay, and also number 6 minus 3.0 and 5% longer is about 2.95 meters. To put here, this is imitate wire number 1, but the value is minus 2.95. This is imitate number 2 minus 2, sorry, minus 2.95. Imitate number 2 minus 2.95. Imitate wire number 3 minus 2.95. This wire number 8 imitate wire number 4. This is without minus but plus. So this is 2.95 without minus. Okay. Now we see the view. Yeah, you see here there is already a reflector at the back of the driven element here. You could draw also manually here, but I think more complicated. Okay. Okay. Now we are going to check the SWR for these two elements now. Start. Yes, the SWR is 5.03. Now we are going to try to optimize to get the minimum SWR. Optimize. The optimized values still the same setting here. Gain maximum for front to back minimum. Elevation here. Okay. Optimizing all elements. Yes. Start. Now from SWR 5.03, down to SWR 4.19. So this is better. 4.19. SWR 4.19 for impedance of 50 ohms. This is the resistance is about 209.5. Okay, this is not matched to the coaxial cable. We should use impedance transformer to match this. Okay, I'm going to explain later. Now we are going to see the beaming pattern now. It is better now. So the power is focused to the front. Now the last part, designing matching system. Okay, you see here at the simulated optimized design, the SWR is still 4.19, or the value, the resistance is 209.5 ohm, and the reactance is minus 0.247 J ohm. Okay, so you have to be able to transform this resistance, especially to 50 ohm, to match it with the transmission line from your antenna. For example, you are going to use RG58 or RG8. So after we design by this program, of course you're going to you're going to realize it in real. According to experience, the SWR value at the realization of the actual antenna would not be exactly the same as this value. So after realize, you should check the SWR at the fit point using, for example, antenna analyzer like that, which could rate antenna impedance exactly, both resistance part and reactance part. Okay, and after that you have to design the matching system. At this tutorial, I'm just going to use this value only. Okay, this is just a approximation. So just click this tool. Okay, you could see here several matching system: LC match, line match 1, line match 2, stop. Okay, I think I like this one, LC match. You are seeing here the frequency at 141.175 megahertz, and the feeder, which is going to be RG58 or RG8 or whatever you are having, as long as the coaxial characteristic impedance is around 50 ohm. And this is a simple matching system, and at the fit point the resistance is 209.54, the same with the calculated here, and the reactance is minus 0.25 ohm. Okay, there are two systems. First, C parallel to the feed point. C parallel to the feed point. This is feed point. C parallel. If you are going to use this C parallel LC-mat system, so the capacitor value unit is 95.7 picofarad, and this series inductor is 1 microhenry. So this is very simple. This program is very smart. Okay, he counts for us. Please remember also the rating of the capacitor and inductor you are going to use, because if it is not accommodating, it's going to be a fire. It's going to be burned. For example, you are going to drive 100 watts to the antenna, so I think the rating of this capacitor and this inductor should be able to handle, yes, around 150 watts, like that. Okay. The rating could be voltage also should be higher than the voltage driven to this antenna. Okay, and second system is C series. You see now this capacitor in series with this feed point. The value here for capacitor, the value here for inductor. Also, you need enough rating.